Okay, so hello everyone. I'm Cai Dieball from the Max Planck Institute in Göttingen in Germany in Alias Codex Group, and I will talk to you about thermodynamic bounds on generalized transport today. And different to everyone else today, I will start with a deterministic, not a stochastic example, and just consider a particle subject to some external force and some medium, subject to some friction, which moves from an initial coordinate x0 to some coordinate xt in time t. And since this system will experience some friction, we expect that there will be a cost of transport. So we will need to pay some energy to transport the system from the one position to the other. In terms of the Stokes friction here with the friction constant gamma, this would be the dissipated heat in the time interval, which we can integrate as force over displacement and obtain this quadratic form of the velocity. And with this already, for this simple deterministic example, we can write down a kind of energy cost of transport of this distance just by using the Cauchy-Schwarz inequality and writing this transported distance as an integral over the velocity, applying the Cauchy-Schwarz inequality. And we see that we have here this quadratic form that is the dissipated heat. And this integral just gives the factor of the time t. And we see that the cost of a displacement from x0 to xt in time t is given by this dissipated heat and this friction coefficient. So, and also, since this is like such a trivial and simple example, now we expect that this will generalize indeed to stochastic systems, even to underdamped dynamics where we don't have many inequalities yet. And also we expect it generalizes to many different observables. And to generalize to stochastic examples and put this in the same framework, we can just know that we can interpret this dissipated heat as some sort of entropy production because we dissipate into the medium and can use this as an entropy production in the medium. So let me come now to set stochastic systems, so underdamped or overdamped stochastic dynamics, where we still have some external force. The same setting basically, but now we have in blue this random term where W is the Wiener process now, and which originates, for example, from these collisions in the medium, which give rise to some stochasticity. And we can ask the same question again. We transport, so we have some displacement from time from position x0 to xt, and we ask the question, how much does it cost us? And now we know it's no longer sufficient to just look at the dissipated energy, because also you get energy from the heat bath via these collisions. But we know, and we have seen today, the thing to look at is now the total entropy production. So this total entropy production can also be seen as a sum of system and medium entropy production. I guess you're familiar. And we can write this as an average. So this brackets is the average over many trajectories, an average value over some local velocity nu, and this friction matrix. And this local velocity nu is just the velocity in the Newtonian case where this entropy production corresponds to the heat, as shown before. And in the underdamped or overdamped case, on the stochastic setting, we get some temperature-dependent contribution here in blue, which also contains this full probability density of the system. And since we don't know this full probability density function of the system, it's been standard, or it has become standard now in the field to look for some inequalities that require less information than this full probability density. And according to the inequality I showed before, based on this Cauchy-Schwarz inequality, we were able to indeed generalize this result to stochastic systems, namely to overdamped and underdamped dynamics. And also, I should maybe stress this holds also for explicit time dependence and transient processes. And what you obtain is this inequality, where on the left-hand side here, you still have this displacement of zt minus z0, where z is now some more general observable, so it can depend on x tau and tau. And here's some contribution if in the case that you have explicit time dependence in your observable, and you get some denominator, which is like a quadratic form of the gradient. And this is bounded by a buff from the total entropy production times the temperature. And you see here for the simplest case, we really have just this bound I showed for the deterministic case before, just with an average value now, which means how this displacement is bounded. And this left one is more general, it also applies to general observables. This denominator here, this encodes how much this observable z stretches the underlying coordinates, and to use this and practice this bound, it's often possible to bound this denominator from just the mean value of z, as I will show later, or also from short-term fluctuations. And I should also stress that special cases of this transport bound, what I call it, are also known in particular for overdamped systems by, you can look at these references. And what I want to show now is an example where the simplest example I came up with is just you consider some underdamped particles equilibrated around 1 in this harmonic potential, could be e.g. due to an optical tweezer. And now at time 0, you shift this potential to 0, and you basically see that the particles will now go to 0, the ones that have before been equilibrated around 1, and you see this underdamped stochastic motion. Here's the equation of motion, and this just is minus a times x, where a is the trap stiffness, is this linear force that drives you towards 0 now. And for this example, we can use our bound. So this transport bound I showed before, the very simplest version again, just for this x. And we know that the total entropy production, just based on the observation of this mean value of x, just the first moment basically, we know from this observation, given the friction constant, what the entropy production must at least be. And then we can plot the quality factor, so the bound we have divided by the total entropy production as a function, for example, as a function of time. And this will always be between 0 and 1. And I can tell you already, I will not show it in detail today, but we can always saturate this bound, so always make it equal to 1 by choosing more complicated observables that, if you want to see this, you can look at these references. And what we see is first in the overdamped case, so this is now the overdamped case, we obtain this black line where we see, okay, it becomes bad for long times, but for short times t, this actually saturates, so it goes to 1, this bound. And we can now also compare to the transient thermodynamic uncertainty relation, because we are in this specific overdamped setting where we have some bounds to compare to available. And here we see for this specific example, the transport bound is always better than this thermodynamic uncertainty relation. If you want, you could interpret this in the sense that for these trajectories I show here, the transport from 1 to 0 basically is more relevant for the entropy production than the precision of this transport, because the uncertainty relation always talks about the precision. Here we really talk about the extent of the transport. We only have this mean value. And if we now move to the underdamped setting, it becomes more interesting. We don't have the thermodynamic uncertainty relation or other bounds to compare anymore, because there are not so many results for underdamped dynamics. And we see that for different frictions, we always start at 0.75 here, so we don't go to 1 for short times. But for long times, for very long times, we approach this limit that we have as expected from the overdamped. And we see that it's also here non-monotonic inference. And the main thing I want to show is really we can do inference now with a kind of good quality factor here for underdamped dynamics, which is a striking new result, I would say. And the other result I want to show, just a different example, is now what we can do because of the form of this transport bound. So I told you before, it only contains these mean values, and other bounds maybe contain the variance or other observables. And this enables us now to look at different kind of experiments that were not possible before. For example, for a scattering experiment, here I put just as an example some Rouse polymer chain under a temperature quench to give rise to transient dynamics. And what we observe at the detector in this thought experiment, we observe the scattering function, which is just a mean value of this Fourier transform, basically. And since we only have mean values in this transport bound, we can rederive this, or we can put in this specific observable into the transport bound. We can do some modifications for the denominator, and we can derive this bound, which only requires measuring the friction constant or diffusion constant equivalently. And then we see from the change in the structure factor, so in the scattering observable, we can get a bound for the entropy production. So for example, if we look at 2 times at this scattering factor, time t 0 and 1, we see from the difference of these two curves that this entropy production we can infer is given by this lower bound on the left-hand side. And actually we see the lower bound is quite good. So it is about 30% of the true value, even though we only measure a one-dimensional projection of this 30-dimensional system here for 3D 10 beats. So just to summarize, we use some unified treatment of Newtonian underdamped and overdamped dynamics to infer the total entropy production for underdamped dynamics, and also for bulk experiments where we cannot measure fluctuations but only mean values. And as an outlook, we would like to relate this to free energy, since we know that this transient entropy production is also given in terms of excess free energies. And we would optimally like to bridge the gap to other fields like protein folding, where they really do these scattering experiments, for example, and other experiments also. Yeah, thank you. And I'm happy to take questions, of course.